All right, so today's lecture is going to be about priority queues, and we're going to build up to its most important implementation called a binary heap, which is often the basis for a lot of systems that need to keep track of things in some sort of priority order. Right? All right, so what do I mean by a priority queue? Well, we're called stack and queue. Okay? So these were two kinds of abstract data types that had very specific semantics, right? So stack we could push and pop on, and queue we could enqueue and dequeue from, and they were kind of limited to this particular queuing discipline, if you will, right? So stacks are first in, last out, and queues are first in, first out. And we saw that we could actually implement these, these particular kinds of queues very efficiently on lists, in particular by using array list, right? I mean, a linked list. So if we have a linked list, in particular one which keeps track of both the head and the tail, so it's just as easy to add to either side, then you can implement stacks and queues very efficiently, because a stack is simply using a list to push and pop from the head of the linked list. And queue, you're pushing on the end because you can add things to the end if you keep track of the tail very efficiently, and then you're popping from the head, right? Or you're enqueuing to the tail and you're dequeuing from the head. I should use the right terms there. Sorry about that. Right, we're enqueuing to the tail, and we're dequeuing from the head. Great. Okay, so there's another kind of queue. So stack and queue essentially are kind of different kinds of queue, right? We call one queue and the other one stack, but really the difference is in their queuing principle, like for how things come into or out of this collection, this line, right? Whether you're first in, first out, or first in, last out. So we can also think of a different kind of queue, and I misspelled priority queue. I made the slides literally just, still working on them right up to the last minute, so they're not very well proofread. A priority queue we can think of, again, as a kind of queue, except instead of being going into and out of the queue based on when you arrive, right? Instead, now you're going to be associated with some sort of priority. So you can think of this like an emergency room, right? Patients are arriving at the emergency room all the time. They don't get seen based on their relative order of arrival of when they got put into the waiting room. Instead, there's some sort of analysis, there's some sort of triage, right? Where they figure out how sick you are or what needs to be done. And if you're a gunshot wound, obviously you have to go straight in. And if you are, just feeling crappy and want an antibiotic, you wait for hours and hours because there are other people who are just more important, right? And so priority queues is this kind of queue where instead of getting things out of it based on their arrival or some relative arrival, we order their way out, we get them back out of the queue by some sort of priority. Now, this actually occurs in lots and lots of computer systems all the time, right? So you can think of processes in an operating system. The operating system is constantly trying to prioritize different processes and schedule them for execution. Deadlines in a real-time system, right? So your anti-lock brakes or your various other flight control systems or that kind of thing. They're constantly trying to decide what the earliest deadline is in terms of what has to get done first and keeping track of what is the highest priority thing to do. And I'm sure you can, if you just try, you could probably think of lots of different situations in which you want to keep track of things relative to their importance, and things arrive to the pool of things to be kept track of with different importances. So sometimes somebody arrives and they're not that important, and sometimes they are important. But whenever you want to select one from who is waiting or that group, you always want the most important one. So that's the idea of a priority queue, right? Now we could sit here and define its functional specification and then its axioms and do that whole rigmarole, and you should be able to do that now, right? So I'm not going to do it in class, but you should be able to do that for such a given a description of what that data type is supposed to work. We'll skip all the way to the code, right? So once, this is essentially the interface that represents a priority queue, right? We want to be able to enqueue values of type V. We want to be as generic as possible when we write these things so that we can use them in different places. So this is going to be a priority queue of some type V, right? So the values, that's the thing that we're keeping track of. And when we enqueue a value, we have to give it a priority. Now, typically, when we describe priority queues, we think of priorities as being smallest equals best, or smallest equals first one out. So, so smallest priority first one out is the rule for a priority queue. There's nothing magical about it being smallest. You can do the whole thing as largest too. It just does, and you just have to have some sort of way of ordering the priorities, right? And so here we're going to model priorities as an integer, and and the smallest one comes out first, right? Right. So when you enqueue, you have to provide a value and the priority, and then internally inside this data structure, however it works, when you dequeue, when you ask for, please remove the highest priority item and give it back to me, you get back some value V, and presumably it's the one that had the smallest priority of anything that was in the queue. I can ask for the minimum value without dequeuing it with getMin, and then I ask for a size. And you can, of course, imagine other useful, non-canonical operations that you might want to include in your data type. But this is basically the fundamentals of what a priority queue is, right? And so, and even size is a little bit dicey. You can get away without it. But the point is that we're going to enqueue items, we're going to dequeue items, we're going to be able to retrieve the minimum item, right? Okay, so that's what we want, right? That's the interface. That's the abstract data type. Now we need an implementation. So how should we implement this, right? If we think back on stacks and queues, we were able to implement those interfaces, those abstract data types, as the appropriate use of a list, right? So maybe that should be what we do, okay? So our first attempt at creating a priority queue is going to be essentially to do it just like we did with stack and queue. We'll use an internal list to keep track of all the items, right? And so let's try this out. So we'll go to the code. Okay. So now I've already completed this. I haven't completed everything. We're going to eventually catch up to what I've completed, and then I'm going to have to go to live coding, so we'll see how that goes. But here is our interface, our priority queue interface, right? And now here is a reasonable first attempt at an implementation of this interface using a list. So I'm going to call that list priority queue. Okay? And so, we'll use list and array list, right? We're going to program to the list, but then ultimately, when we create the list, we need to create a particular type of list. I'm going to choose array list. It turns out array list, linked list is going to be just the same either way once we kind of investigate how this is going to work, right? But my priority queue, my list priority queue of values of type V implements that interface. And here's how I'm going to do it, right? I'm going to have a list of values and a list of priorities. Well, because I have to keep those things together, right? I have to know both, right? In order to know which one is next. And when I create a list priority queue, it'll create array lists for those things, right? The values is array list of V because this is a list of priority queue of type V, right? The priorities we know are integers, right? Because that's part of our this was our interface. Is our priorities are going to be integers. So we can go ahead and fill in integer there. We know that this is going to be a list of integers. And to enqueue easy peasy, we'll just add it to the end, right? That's actually pretty efficient for array lists, right? We've chosen to use array lists here, but it's pretty easy for array lists because adding to the end for array lists is an order 1 operation, and that's that's good, right? You would think that's excellent. But when we need to get one out, that's where things start to get a little dicier, right? Or not dicey, just not as efficient. So now we need to find the smallest item in the priority list so that we can figure out what index it is, so that we can then retrieve or remove the appropriate item in the values list, right? We have 2 lists, one for values, one for priorities. This isn't all that hard. The first thing we need to do is make sure that this is legal. If you have an empty priority queue, right? If you have an empty list, you can't ask for the next highest priority thing. There is no next highest thing. So, we're going to basically define, right, as undefined, and that's actually, like if you did the axiomatic specification, that's exactly, it would tell you that that has to be true, because you would have to sit there and construct a right-hand side for the left-hand side of applying DQ on a new empty list, right? That's the canonical operation, and so you have to define that axiom. There is no good definition for that, and so you would say, oh, that's undefined. That should not be allowed. In Java, when you come to a situation that should not be allowed, integer, you're trying to index an array out of bounds, you're trying to divide by 0, you're trying to take the next item from an empty priority queue, you throw an exception. That's how we signal undefined in code, in Java code, right? And so we're going to use a standard unsupported operation exception. This is an exception type that's built into the Java library. So no great shakes there. Otherwise, we need to find the minimum index. So we'll, I'm going to imagine that there's some helper function called find minimum index that will give me back the index of the minimum priority. And so now I can remove that value from the values list and capture that as the result. And because my values list and my priorities list, we need to keep them in sync, right? If I'm going to take something out of the values list, I have to take the corresponding thing out of the priorities list. I'm going to remove that. I don't need to capture the value because I don't have to return it. And so dequeuing just finds the minimum index and returns that result. Getting the minimum, same deal, except now after I find the minimum index, I just have to retrieve that value from the values list and return it. I'm not changing either list because I'm not actually dequeuing it yet. And then size, well, that's just the size of the list, right? The 2 lists should be exactly the same size. We put things on them in the same, at the same time. We take things off of them at the same time. So values and priorities, it doesn't really matter which list I choose. I can just get the size of either list. That's the size of my priority queue. And then finally, in order to make all this work, right, these were the public, this is the implementation of the various things that being a priority queue demanded we do. And then we had one private helper function called findMinIndex, where, again, I should never be calling this unless there's at least one item, and so I'll test for that. I don't really have to test for that, because if you look back on the code, you'll see that we never call findMinIndex unless we're already at a place where we've confirmed that the list is the size of the priority queue is greater than 0. But belt and suspenders, why not? And then basically, now that we know we have at least one item, we'll pretend that the first item is the minimum item, and figure out how big it is and keep these in temporary variables or local variables, while we then run through the rest of the list, starting at 1 now, up to but not including the size, right? That's how we run through 0 to n-1. And if any of those things are smaller than the min I've already found, update my local variables for the new minimum index and the new minimum value, and at the end of the day, return the minimum index. Okay? All right, so we ran through that pretty quickly, so this is probably a good time to stop and say, does anyone have any questions about how I wrote the code to implement a priority queue using a list? Good. Right? Hopefully that was relatively straightforward, right? Okay, so let's think about whether or not this is useful, right? Right, so, how efficient is that, right? Well, let's think about this, right? When we NQ'd, right, that was pretty efficient because we could just put it at the end of the list. So that was order 1, that's great. But dequeuing required us to search for the minimum thing, right? And so that was order n, right? If we analyze this data structure, basically saying, well, look, it's only useful if we're going to put things onto this thing and then take them out in order we know which one is the highest order. So we can assume that for any n items in how we use a priority queue, we're going to NQ n times and we're going to DQ n times. So in order to work with a problem of size n using a priority queue, we're essentially order n squared work, right? The NQing all takes order 1 time times n items, that's order n, and the dequeuing takes order n time on average times n items, that's order n squared. So not particularly great, right? Not awesome. So maybe we can do better, right? But before we go off and do better, I want to take go and revisit the code from a coding, programming, Java technique point of view before we switch back to data structures, just briefly, right? So regardless of efficiency, our implementation of that list, right, that list-based solution to a priority queue, could have been a lot better. In particular, right, if you look at it, we have 2 lists, one for values and one for priorities. That's fine. Look, I mean, I'm not saying it won't work. It does work. It works relatively straightforwardly. So it's not like it's the worst implementation in the world, right? But from a pure object-oriented kind of programming elegance point of view, right, it's a little hinky, right? And the reason why is because these 2 lists aren't really 2 different things. They aren't really independent. I have to add things on them together. I have to take things off together. The ith thing in one list corresponds to the ith thing on the other list. They're really just one list with 2 parts, a value and a priority. So it'd be nice if I could glue those 2 things together, right? And make something that is the value with its priority, and then use one list for that, right? This is a pretty standard thing to do in programming. It comes up a lot. And there's a lot of, there are different ways than this to do it. But let's try to change our solution to glue those 2 pieces together. So this is going to be take 2. And now this is, right. So this is where we've caught up with my pre-coding, and now we're going to kind of do this live, right? So the first thing I'm going to do is, like, take 2 is exactly the same as take 1, all right? So it's a priority queues of values. It takes a value and an integer, and then dequeues and all that business, right? And then this is our implementation from what we just did. Okay, so we haven't changed anything yet. The goal here is that what we'd really like to do is glue, each value with its priority and keep one list of something that was a value with the priority. Okay, so to do that, what we can do is we can start off by creating that interface, right? That describes what that would look like, right? So I'm going to call this prioritized, right? VNP. So what I'm doing is I'm creating an interface, right, which is a prioritized, right, a value with an integer. Okay, so something that is a prioritized value, right, has I'm sorry. I'm skipping ahead, unfortunately, so I'll do it this way. So I want a prioritized value, right? So a prioritized value is just like a value, right, whatever a value is, but it also, right, is attached to a integer priority value, okay? And that's why I'm calling it prioritized value. What would a prioritized value be able to do? Well, it should be able to retrieve the value, right? That it's, the value part of a prioritized value. So we might imagine that, oh, it's going to have a get value, right? In order to retrieve the value. We might actually want the priority as well, right? So we know that's an integer. So we're going to say get priority. So that's the priority that we get with it, right? Do we need anything else? Yeah, maybe that's it. We'll just stick with that right now. Okay. Now that we have this prioritized value interface, right? We can create a implementation. Okay. Which implements prioritized value implementation, which does so on type V, right? Implements a prioritized value. Great. And it's complaining, says, well, if you're a prioritized V, then you have to have a get value and a get priority. So I have it auto-generate those things. I need to be able to create one of these things, so I need a constructor. So I'm going to say, OK, a prioritized value takes in a V value and a integer priority. I need fields in order to store these things in an object, right? So, and I want to keep them private. So private v value, private int priority, and we'll say value value equals value, priority equals priority. And most of this just kind of writes itself, right? Oops. Return value. And return priority. Awesome. Okay. It does, doesn't it? Hold on. Prioritized. Why is this? Return type for the method is no, because that's, did I spell? Oh, impl. Oh, sorry. OK. So now we have a way of gluing the value and the priority together. The nice thing is now that we have this way of gluing the value and the priority together, we can change our implementation, right? So instead of having a list of values V, right, we have a list of prioritized values. And I don't have to have this separate list, right? Now to create in the constructor, instead of creating a new array list of values, we're creating a new array list of prioritized values. And I don't need this guy. To enqueue a value and a priority onto my list, right, to add, now I have a list of prioritized values. I've been given a value. I've given a priority. I can now glue them together into my new, my new prioritized value type and put that on the list instead. So I can say, new prioritized value of type V, and the constructor takes a value and a priority. So that's going to glue those together, and it adds to the one and only list I have. Now to dequeue, everything looks pretty much the same. Size equals 0, IDX still equals min IDX, but now I'm going to, the result is going to, now I can actually just return the result directly. But the result is now, when I remove that IDX from values, I'm getting back a prioritized value, and from which I can kind of grab the original value that I glued with the priority because I don't need the priority part anymore. That's my results. If I'm going to just assign result just to return it, I might as well just return it. Get min, now same thing, except once I get that value, I'm not getting a value anymore. I'm getting from the list a prioritized value, and so I have to unwrap it and get back to the original value. Size remains the same, and min IDX now. I don't want to keep which integer. I want instead. I want to keep track of what is my minimum prioritized value. So my prioritized value v min equals whatever at 0, which is values.get 0. Great. And for I equals 1, going through all of my values, if the values at that, right, that's going to get back a prioritized value. Then I can say, does it get back the actual priority? If that is smaller than min.get priority, why is this guy not good? Prioritize value. Oh, because I didn't import prioritize value? No, I shouldn't have to. No, hold on. What's going on? Oh, prioritized value there. Oh, not it. Prioritized value. Oh, this should be impl, that's for sure. You're correct. But it still doesn't like it. Why am have I misspelled something? Prioritized. Yes, thank you. And then over here, find priority. No, it shouldn't need to be impl because what's coming out of the list is a list of prioritized v. And so this should be, this is just not prioritized value, just prioritized v. That's it, right? Prioritized, it's a prioritized value, right? We want to program to the interface, right? That's why we don't put impl there. When we create a new one, we obviously have to say impl. We have to have a specific implementation. But when we're using it, we should use the interface. So that's the minimum. And then we now check against the priorities. And if that's, right? And now we're only keeping track of one thing, which is a lot nicer. Right, we're keeping track of the prioritized value, and then when we want to return the index. Oops, we do need to keep track of the index, of course. Oops, sorry about that. Int min idx equals 0. Min idx equals I, and then return min idx. Yes, no, that's true. But now, our prioritized value is our value and our priority together, and so we use it. So this doesn't change anything, right? I mean, it's still not a good way to do a priority queue. But I did want to kind of show you this idea that often inside these data structures, we have to glue this general piece of information that the data structure is supposed to be handling with meta information or side information that our data structure needs in order to keep its implementation working, right? And so one way to do that is to essentially follow this pattern where you create a new interface in the general type along with the extra information you need, and get getters for that, and then an implementation which is just essentially the value wrapped with that extra information, and then you make your data structure work internally in the parlance of that glued together kind of data structure, right? But then it's interfaced to the rest of the world for dealing with that general value, right? You can unwrap it as necessary and wrap things as necessary when they come into the data structure and then back out. So here, the values come in with this integer priority, and that's what we're trying to organize our list by. So we glue them together to create this new kind of thing that's carrying its value and priority together. And then when we have to dequeue it, we only want the value part, but we deal with it internally as a prioritized value, and then when we actually need to get it all the way back, we kind of unwrap it and get back to the original value. Okay. So that was a little bit of kind of just good best practice in terms of software engineering. The actual data structure still is no better, right? And we don't really want to use it that way. Okay, so what do we want to do? Well, what about a binary search tree? Okay. The problem with doing a list was that finding the minimum every time we needed to dequeue something was an order n operation, and that's what made our overall performance order n squared. A binary search tree might be something that we think about, and is something that you are currently programming, so maybe that works, right? If we assume the average case, right, for a binary search tree, then it'll be order log n to in q, right, because we have to drop it down to the appropriate leaf and add it at the end of our binary search tree. To dequeue is pretty easy too, because we have to find the minimum priority. So we can just go left until we get to the minimum prioritized value, right? So this is why I wanted to do this gluing thing together, because it's one thing to keep two lists together and synchronized. It's an entirely different thing to keep two binary search trees synchronized, and it's kind of a pain in the ass, right? Because, right. Anyway, so that's why we need to glue values and priorities together. So we can enqueue in log n time. We can dequeue in average case log n time. And overall, we'll get this n log n performance, which is better than n squared, certainly. But the worst case here could be pretty bad. And the reason why is because the structure of our binary search tree is going to be determined entirely by the priority numbers and the order that they come in on, right? And so if the priorities come in relatively, already well ordered, right, we'll end up with these long binary search trees that essentially turn into lists, and we might get order n squared performance all over again, right? And that's no good. So, if we think about it, like, okay, I know that the list isn't going to work, but the binary tree idea is not a bad one, right? Because it does allow us to kind of cut the work in half. The enqueuing part, and the dequeuing part on average is good, right? We'll beat our list. And so is there any way to make it so that instead of the average case and a worst case, that we actually have the worst case be the same as the average case, that we never do worse than n log n, no matter how the priorities come in, right? That would be awesome, right? And so the insight here is our binary search tree is doing more work than it really needs to do. Because basically, we never really need the ith biggest item. The binary search tree is great for search, either finding something that's in the binary search tree, or just seeing if it's there, or finding a particular ith item, because we can do a depth first search, or that kind of thing, right? Find our way to the a specific leaf, right? In order log n time. But that's more work than we really need. We don't really need to keep everything in order, right? We just need to know what is the smallest thing in the tree, right? And if we just need to know what the smallest thing in the tree is, maybe we can use that in order to get rid of the other problem that our binary search tree has, which is that the trees could get unbalanced, right? So if we think about a binary tree and retrieving that has, comparable items in it, right? And retrieving the thing that is smallest, where would we want that thing to be? Where's the easiest thing to retrieve from a tree? The very top, right? If I know that the minimum thing is at the very top, then I don't have to go anywhere. I have an order 1 lookup for the minimum thing. That's got to be, that's awesome, right? I might still have, I might have to do some work to fix my tree, but at least I can get to the minimum thing really, really quickly. And that is the idea of a binary min tree, right? So the only difference between a binary min tree and a binary search tree is the invariance, right? I talked about invariance before, kind of being, almost like rules for how a data structure with certain semantics would have to work, right? So rules that we could always check and we could kind of build our algorithms around, right? So for a binary search tree, the rules were that everything on the left-hand side tree was smaller than the value at the top of the tree, the root value, which was smaller than everything on the right-hand tree, right? And what was on the left is a binary search tree, and what was on the right is a binary search tree. And with those rules in place, we knew that our binary search tree would work the way we wanted it to work, and so when we put something into it, we knew exactly where to go. When we're looking for something, we knew exactly where to go, and that kind of, that drove all of our algorithms for how we worked with our binary search tree. We can think of a binary min tree in exactly the same way. They're just different rules, right? And so the rules for a binary min tree is the value at the top is smaller than either the values on the left or the values on the right. And that's it. We don't need any other rule. We don't need everything on the left to be smaller than everything on the right. We just need everything below us to be bigger than the thing that is at the top. Right? So that's one rule. The other rule we want, which is going to address the unbalanced tree thing, is that however we put things into the tree, we always want to make sure that the height of our left subtree is at most differs from our right subtree by at most 1. In other words, the height of our children are never more than 1, unbalanced by a value of 1. Right? And so, and then the last rule is that the left and the right, are both binary min trees themselves, right? Does that make sense? Hopefully, right? And so, okay. So with those rules, now we can always know where the top is, like the top is going to be the highest priority item. That's great, right? But now we have to make sure that our invariance, if we remove that item, that however we fix our tree, that the invariants still hold. Now, before we get to the code, we can even just having with that binary min tree idea in mind, we can talk about its performance, right? It turns out it's still order n log n, right? We didn't really make it any faster than using a binary search tree, right? But what we did do is make it so that it was always the same. Right? In other words, it was like there is no average case versus worst case. It's order n log n in the worst case. And the reason why is, and we'll see this, is because when we enqueue, it's just a matter of inserting into the tree, and the rules there are pretty simple, right? And we'll see how we can, if in terms of deciding whether it goes at this root or to the left or to the right, and we'll see how this goes in the code, right? But it turns out that is an order log n operation. When we dequeue, it's an order 1 operation to find the right one, because that's at the top of the tree, but it turns out it's an order log n operation to fix the tree back to being a binary min tree, right? Dequeuing is still an order log n operation. And then if you do this n times for a problem size of n, you get n log n as your overall performance. However, right, but that is guaranteed, and it's guaranteed because of one of the invariants, that the left and the right are never unbalanced by more than 1, right? So if because of that invariant, we know that these things are always going to be log n operations and never possibly anything longer, right? So we've eliminated the worst case. That's nice, and we'll actually see it coded up. I will, however, caution you, and this is going to take us between now and also on Thursday, so we're not going to finish this. But I will caution you that it turns out that no one's ever uses a binary min-t in order to do a priority queue. Instead, they use something called a binary heap. But I want to go through the exercise of coding the binary min tree in order to, because I think it's worth, I think it has some teaching moments in it, before we then go visit what a binary heap is. One point of nomenclature, you see the word heap here, and we've talked about the stack heap model of execution. Two different things entirely, okay? Have nothing to do with each other. And it turns out that a binary heap structure is essentially a binary min tree. It effectively is a binary min tree, except that it's able to be used, you're able to implement it very efficiently with a list, and very easily in a way that you would prefer, because your memory is a little bit more local, and we'll talk about what that means later, and it's less prone to mistake. And so no one's ever going to use the binary min-t for priority queue. We're going to use binary heap, and we'll see that probably on Thursday. But for the rest of today at least, which is what, 5 minutes? Is that 5 minutes, or do I have longer? Hold on. No. Oh, good. Excellent. For the rest of today, at least, we'll go through the implementation of binary min tree. I was about to get really scared because I was like, oh, no, I'm not even close. Right. All right. OK. So let's do this binary min tree then. All right. I'm going to do this again. I'm going to try to do some of it live, and then we'll kick over to the completed code that's in this lec15 package if we have to. All right, so I'm going to say lec15 take 3. Oops. What I want is a package. lec15.take 3. OK, I'm going to copy my priority queue interface. I'm going to close all the files so I don't get confused. OK, the very first thing I'm going to do is I'm going to generalize a little bit further. Right? I am the king of generic code. I think anything can be written generically, and then the program is really just a generic instance with the appropriate types applied. So the way we're going to do this is we're going to have, there's one more thing that we can make generic. Like we said, oh, we're going to have these priorities that are going to be integers. They don't really need to be integers. In fact, it'd be useful if they could be anything that is comparable. That's right. As long as it's comparable, then then we can use anything as a notion of priority. And so the person who's using, or the programmer who's using your priority queue implementation would appreciate the fact that it had a more general version of priority. So instead of enqueuing a value with a integer priority, we're going to say, look, I don't know what this is. Right? It's some type P, but I do know that it extends comparable, right? In P. Okay? Everything else stays the same, right? So all I did was generalize my int to be some unknown type P, which when somebody wants one of these things, they'll tell me, and that type P had better be comparable, because that's the whole point, right? OK. And so now we're going to implement this priority queue. We're going to create a binary min tree, which is an implementation of this kind of priority queue. So we're going to say, OK, I'm going to need a new class. Right? And I'm going to say I want a binary min tree. Right? Now, a binary min tree of what? Well, of some sort of value v and some priority type p. Right? And this implements, right, a priority queue of type v and p. Oops, that has to be capital V, right? Capital V. And there's a limit, there's a restriction on this type P when it's specified. It has to implement, it has to extend comparable of P, because otherwise I can't compare anything. OK, great. OK, you promise to be a priority queue. You better have these methods. OK, great. Now, what's a binary min tree? A binary min tree is a root value and 2 more binary min trees, right? And so when we did this with binary search trees, right? So when I assigned assignment 5, I made a very specific decision to make your recursive algorithms a little bit easier, which was to tell you to model empty trees as a different kind of object than a tree that was not empty, right? So our assignment 5 creates, has these 2 different implementations of binary search tree, an empty binary search tree and a non-empty binary search tree. And at the bottom of the non-empty binary search trees, at the leaves, right, at the things at the bottom of those trees, were non-empty binary search trees whose left and right happen to be empty binary search trees. And that's what defined being a leaf, right? You were basically you had 2 empty children. But the reason why we did that instead of using null, which you'll see a lot if you Google this kind of stuff online, right? You'll see people using null to mean an empty tree or an empty list. I hate that shit. And the reason why is because it's not, right? Null should not be a valid value, right? There is such a thing as an empty tree. Model it. Right? And so, and we saw that there was some value to it, right? Because it naturally became our base case for all of our recursions. When we're asking for the height, the empty tree had a well-defined answer, -1, which allowed the leaves to find the max and add 1 and properly get 0. And so we were able to we didn't have to detect that special case. It was well-defined for both empty and non-empty binary search trees, right? The other nice thing about doing it this way is that your insertion recursion also worked. Because if you were non-empty, you figured out which side you had to go on and insert it on that side, right? The search part, right? And then once you got to the very bottom to a leaf, right? You basically saw which one was smaller and inserted the other one to the left or the right. But the point is that you inserted it into an empty tree, and that empty tree became a new non-empty tree, right? And had its own empty leaves underneath it. Now, in order for that to work, I said, hey, usually in object-oriented programming languages, we expect our objects to mutate. Usually when we translate our functional specification of our data type into an object design, anything that is operating on an instance and then just kind of creates a modified version of that instance, all those functions were supposed to be void functions because you're mutating that existing thing. Now, it doesn't quite work that well, if we're modeling empty trees separately from non-empty trees because there's a little hiccup there. And the reason why is because, yes, most of the time we can just mutate the tree that we have, great, right? But sometimes the very object itself needs to change types. If I have a tree that only has 1 item in it and has a root value and 2 empty trees underneath it, and I remove that item, then unfortunately I can't change this non-empty tree in some way to make it empty. I need a completely different type of object, an empty tree object, to represent being empty. Similarly, if I am at the bottom of an insertion and I'm trying to insert into an empty tree, I need to replace that thing with this new non-empty tree. And so inserting into an empty tree, the result of it needs to be that the object itself changes into a new kind of object. So because of that, right, basically it's type mutation. There are certain operations that need to not just mutate the object, but mutate the type of the object. And because of that, we did a little fudge thing. We said, okay, yes, Java wants our mutating methods to be voids, right? But in this case, because we want to model empty trees as a separate kind of object, we're going to do some hybrid thing where inserting or taking out of a binary search tree or removing from a binary search tree would produce its own replacement, right? And so when we used insert or remove, we would say, like if I was inserting into my left child, I would say, left equals left.insert, knowing that the left.insert would result in the appropriate tree, which is the left tree after having this insertion be done, right? And I could assign that right back to left, right? And that allowed us. So if that object was able to mutate and change itself, great. It would just return itself, right? But if not, then it would return this new version of itself, which was this whole new object. But either way, it's okay because I make sure I return that result, and I capture it back into, I replace that field with the result. And so that's how that would work. And so that's how assignment 5 worked. I want to show you an alternate way of solving that same problem, but without having to require type mutation. And basically the idea here is that we're still going to model an empty tree, except that we're going to do so all in one type. It's not quite as clean or as nice as modeling empty trees, at least in my opinion, but it'll get us out of a jam later on when we need to, when we need two things out of our return value and we couldn't do it otherwise. So you'll see. But the point is that in this implementation that I'm about to go through, right, we're going to take a different tact for empty trees. Instead of having a specific type of object for empty trees, we'll still have an object. We'll still never really use null as a valid anything, right? But we're going to we'll have to model emptiness explicitly inside our object. Okay. So with that, right? We need a binary min tree is going to need a constructor, right? Well, it's going to need instance fields. We'll start with that. So it's going to need some private field, which is its root value, right? And that's of type V. We know that. And in fact, we're going to do the exact same thing we did before, which was to glue our priority with our value. And so really, we need a prioritized value V as our root val, right? Now, hold on. Where did prioritized come from? Let's go ahead and copy it from before. Prioritized and prioritized value impl, right? And I'll paste them here. Now, if I go to prioritized value impl, I should have just said prioritized impl instead of value impl. That was kind of dumb, so I'm going to change it here. Prioritized impl. So I have prioritized, and that's my prioritized here. Now here, when we did it prioritized here, we assumed that the priority was an integer. And now we're no longer doing that, right? And so in fact, in my binary min tree, right, it's not a prioritized, in my prioritized, it's not necessarily an integer. It's anything that can be modeled as a priority, right? Like in my priority queue, it is whatever this P is that's comparable. So in my prioritized interface, I need to, again, generalize that integer part. It's not necessarily a prioritized value, and I know it's an integer priority. It's a prioritized value of some priority type P, and I have some priority type P. Okay? And not only is it P, that P needs to be comparable, right, to other P's, right? Great, right? And so prioritized impl, right? Same thing. Now it's not just V, but it's V and P, right? And it's not O as an integer. It's just whatever P is, and I'll get whatever P is, and I'll return whatever p is. OK, so I fully generalize my idea of a prioritized value p. I also need to remember it's not just p, it's a p that extends comparable. Great. OK, so that's my prioritized impulse. I've updated those so they can be kind of generic. Back to my binary min tree, right? So now my root value is going to be some prioritized value, right? OK, and I'm going to have a left, which is a binary min tree of this v with this p. That's my left, right? Because this is a recursive data structure. I have a left and a right. Right? I need a constructor. I need to actually initialize one of these things. So I have to have a public binary min tree constructor. And that's going to essentially, let's say, and so now, OK, so this is where we get to our problem, right? Sometimes we want to construct an empty version of this tree. Sometimes we want to construct a version that's not empty. In the assignment, we had two different classes, so we never had to we could write one class and it knew exactly what it is, empty or not empty, and it could answer all the questions correctly. Here we're going to have one class that does both jobs. It needs to represent empty trees and it needs to represent non-empty trees. So I need to have a way of knowing whether I'm empty or not, right? And so, and then I need to have a way of constructing empty versions of myself or not empty versions of myself. So we'll assume the one that doesn't come with any value, right? That's the one that's going to create empty versions. If I want a non-empty version, then I have to provide a root value, right? And then I'll create my non-empty version. But let's create the empty version first, right? Something about we need something to be our signal that our tree is empty. Do not say set root value equal to null. Wrong, right? Now, I'm not saying that we won't set root value equal to null for an empty tree. It just should not be how we tell. And the reason why is because we don't know how our data structure is going to be used. Maybe somebody wants to insert null with a certain priority, right? And so, so well, actually, this is a value glued with a priority. So we would, so that actually we could use root value equal to null. But personally, I think that those kinds of magical kind of if this is null, it's really this other kind of thing. I personally find that somewhat distasteful. I would rather model it explicitly, right? So I'm going to model it using a Boolean, which is empty. Okay? And so if I create an empty tree, then isEmpty is true. Okay? And it doesn't matter what anything else is, because isEmpty being true is going to be the end of the story. Right? I can and probably should set root value and left and right all to be null when isEmpty is true. But the cool thing is that if I'm doing this really correctly, I shouldn't have to, because isEmpty tells me everything I need to know. If it's empty, then nothing else matters, and and if it's not empty, then everything else has meaning. Right? But just to be kind of good about it, I'll say, OK, and root value equals null, and left equals null, and right equals null. But I'm not going to use that fact as the indication of it being empty. I'm always going to use isEmpty as being the indication that it's empty. OK. So when we want to enqueue a value with a particular priority, what do? Right? Oh, no, let's create the other constructor first. Public binary min tree, and I'm going to be given a value and a priority p priority. All right? Oh, actually, yeah. Is that what I want to do? No. I want a prioritized value, because this is all going to be part of my implementation of the priority queue. I'm not, the priority queue has its interface. This is my binary min tree, which works on prioritized values. So it's going to get a prioritized value V and P, right? And that means that the root value is going to be this value. And my left is going to be a new empty binary min tree, right? And my right is going to be a new binary min tree in V and P. Forgot. Right? There's going to be empty. And, of course, is empty is false. Great. OK, so now when I want to NQ a value onto this tree, remember what my invariants are, right? My invariants are the thing that's at the value is, if I'm not empty, the thing that's at value is always bigger than everything in my left and everything in my right. Or always smaller. It is the smallest thing in the entire tree. So I need to put this new value, and if I have and my left and my right are never different in terms of their height by more than 1, right? They're balanced, right? Those are the two rules. So to NQ a new value into and with a given priority, first I need to create a new prioritized value, right? So I'm going to have a prioritized, because my tree works in prioritized values, right? Value. B comma P equals prioritized value equals new prioritized value impl given the value and the priority. All right? And now I want to put it in my tree, right? OK, so I need this NQ to have this signature because it is part of being a priority queue, right? I need to be able to take in a value and a priority and NQ those together. So first I glue them together, but I really want to do then is to NQ them, insert them into my binary min tree, right? And so I'm gonna that has nothing to do with priority queue, right? Priority queue is that's the interface. Here's the value and the priority. Go do what you're going to do with them. What I'm going to do with them is glue them together and then insert them into my binary min tree, right? So I'm going to imagine that my binary min tree has a way of inserting new values, right? That are new prioritized values, right? We can think of it as NQing new prioritized values. So I'm going to say, oh, OK, I'm going to then NQ a prioritized right? So I'm going to have this NQ here that takes the value and the priority separately. That's part of my public interface of being a priority queue. This NQing my prioritized value, right? That's an internal behavior of putting it into the tree and maintaining our invariants, right? That's how we're implementing the priority queue. So that is not public behavior because it's not part of my priority queue interface. It's private behavior. So I can imagine that I'm going to have some private function for NQing the prioritized value. And this is a prioritized. Oh, it's just prioritized. I keep putting value there when it's not prioritized value. It's just prioritized. This should. OK, so how do I actually put it into? So this is really just kind of a thin veneer, right? The implementation of the public interface is really just a thin veneer for creating, gluing them together, and then delegating to some internal behavior, which is actually going to put it into our tree. Jesus Christ, is it? Oh, it's because I took out value. There you go. All right. Okay, so how do I put it into the tree? So this is the actual work of putting it into the tree. Well, I look at the priority associated with the thing I'm trying to put in the tree, right, with the thing that's already at my root, right? This is for a non-empty tree. And if the priority of what I'm putting in is smaller than what's already at the root, then this is the home of this item, right? If root is the smallest thing, and not only here and everything below it, and now the thing I'm trying to put in is smaller than root, then this is where it belongs. So what I'm going to do is I'm going to switch places. I'll say, aha, I'll put what I'm trying to put in, I'll put it here. And I'll take what used to be at root, and I'll put it into one of my children, right? And then my invariant still holds, right? Because what's at the top is the smallest thing, and it is smaller than either the things that are in either tree. That was true before with the root value. This new thing is smaller than the root value, so if I put it here and take the root value and put it somewhere below, it'll still be true, right? And so that's how I'll hold on to my invariant if what I'm trying to put in is smaller than what's at root. If what I'm putting in is not smaller than what's at root, then I just, the invariant still holds, and now I just insert the thing that I'm trying to put in into one of the children. So I choose which child do I choose. I ask each child, what's your height? If one is bigger than the other, I put it in the smaller one. And if they're equal, I put it into, it doesn't matter, let's say I put it into left. I just break the tie. That way, height will never be off by more than one, right? As soon as one of your children has a longer height than the other, then the next insertion is going to go into the other child. And it'll continue to go to the other child until they're equal, and then the next insertion will go into left. That might make it longer, it might not. It's certainly not going to make it shorter, but if it does make it longer, then the next insertion will go into right? And so what we'll do is we'll fill up our trees evenly. We'll put one in left and then one in right, and then we'll put another one in left, and we'll keep putting things in left until left completely fills up, and then then it'll get one deeper, and then we'll start putting things into right until it completely fills up. And then it'll get one deeper, then they'll be tied, and then we'll go back to putting things into left until it's one deeper, and then back to putting things into right until it's one deeper, and we'll grow our two children, right, evenly, right? And so that's what we'll do with non-empty trees. For an empty tree, that's easy, right? Putting something into an empty tree makes it a leaf, makes it a tree, right? We put it here, and now we have two empty children. We just turn ourselves from being empty into being a non-empty tree. So when we in Q prioritize, we first ask, are we empty, right? If we're empty, and I'm going to just assume that I have if is empty, right? If we're empty, then become non-empty, right? This is where you go. So your root val is the value that you're trying to put in here, and your left child, did I call it root val or did I call it root value? Your root value is the value, and your left child is a new empty tree, which is just just all this basically. Right? So your root value has a value, your left and your right are empty trees, you are no longer empty, right? Great. And that's what you do if you're empty. If you're not empty, otherwise, right? Now we do the comparison, right? We can say if my value.getPriority dot compare to, because it's comparable, to what's at root value dot get priority I always have to see for myself, right? If those two things is less than 0, right? Okay, then I know what I'm trying to put in is smaller than my root value, so I will swap the two. I'll say, okay. Temporary equals value, value equals root value, and root value equals temporary. So I swap the two. So now at this point, right, I know that value has the smaller of either root value or its original self, right? We were trying to put in value. We got to this spot. Value is smaller than root value, so we switched places. And now we have a value that is bigger than root value, and so we need to then insert into either left or right. And now we need to know what height they are. So the trees need to be able to report their height. We haven't written that code yet, but we can imagine that that is something that they can do. So then I say if left.getHeight is less than or equal to right.getHeight. If it's a tie, we'll favor left. Then insert NQ prioritized. See, this is the nice thing, right? Because the value, right? NQ prioritized into left. And then otherwise, NQ prioritized into right. And then we're done, right? Okay, so that's NQ prioritized, right? So let's see, we're looking at time. Okay, great. So this is let's go ahead and quickly do height, right? So height is something that we imagined existed for our binary min tree because we needed it here. So let's go ahead and do that. Now, usually what we would do for height is take the maximum height of left and right, and then take the maximum of those two and add 1. The problem with that is that means that you have to constantly travel to the bottom of the tree to find the height of the thing. And so we want to make that faster. An easy way to make that faster is to actually model the height explicitly as one of our fields, but then we have to be careful that we make sure that it's legal all the time, right? So we're going to say, okay, we have an integer, which is our height. And if we have an empty tree, we already know this trick. Height equals -1, right? So it is a valid value. It's just -1. It'll make it so that the leaf calculates the right height correctly. And if it's a non-empty tree, and if we create a non-empty tree, this is creating a leaf. We know that, right? It creates a value with 2 empty subtrees. So we know its height. Its height is 0. So that's how we initialize height. Whenever we NQ something, right? We don't necessarily know that we're any, and we're, whenever we NQ something, we're just, that's just delegating to this NQ prioritized. And then in NQ prioritized, if we NQ it into an empty tree, then we need to make sure height is correct at the end of the day. Height equals 1, right, or 0, right, because it went from an empty tree to being a leaf. And then otherwise, if we NQ'd into something that wasn't already, that wasn't empty, then we either put it into our left or our right. I'm not sure where it went. I know where it went, but I'm not sure what it did to its height. So I have to recalculate my height. And so I'll say, and after I've done this, height equals left's height. The maximum between, right, math.max between the left height and the right height plus 1. And we know that'll work even for leaves because of how we did that whole -1 trick. And then now the last thing we need to do is add our getter for retrieving height. And that is simple because we're modeling it explicitly, so we return height. Okay. We will pick up the rest of this on Thursday, but are there any questions about how we got to this point, how NQ worked, and kind of where we're going with this? All right. So we'll pick it up here on Thursday. We'll finish the binary min tree, and then we'll actually see how it's really done for real with a binary heap. And we'll look at how a full binary tree can be modeled inside a list, which is what binary heap does.